The easiest way to send information through a wire is to turn the current flow on and off in a sequence. On and off are two states, which can be represented as a 1 and a 0. That's what computers use to communicate with each other, bits. We call it a binary system because it uses only two states. It's a base 2 system. In our daily lives, we use a base 10 system, which uses 10 different digits, 0 to 9, 10 states. That's why it's called a decimal system. To understand how counting in binary works, we should first understand how counting works in base 10. We start at 0. Each time we add 1, we go to the next digit. There is no next digit after 9, so what do? We go back to 0 and add 1 to the 10th digit. We continue like that until we fill the 10th place, and then we add 1 to the 100th digit. That's how we count in decimal, and that's also how we count in binary. Start with a 0 and go up by 1. In binary, there is no next digit after 1. Those two are everything we've got. So again, we go back to 0 and then add 1 to the 10th place. But since it's binary, it's not called the 10th place, but a 2's place. We continue like that until we fill the 2's place, and then we add 1 to the 4th digit. We continue adding, and when we fill everything with 1's, we increase the 8th place. Why 4 and 8? In base 10, we have the 1's place, 10's place, 100's place, 1000's, 10,000's place, and so on. Those are all powers of 10. So in base 2, we use 2's place, 4's place, 8's place, 16's place, and so on respectively, because those are all powers of 2. Okay, so we know how to increase a binary counter by 1, but how do we decode what's that number's value in decimal? All we have to do is take the bases of bits set to 1 and add them. Here's another example. But why does that work? Let's go back to what we know, base 10. If we see a big number, for example 2501, we know it's made out of 2 thousands, 500s, 0 tenths, and 1 1. We can think of them as bills. So in binary, if we see 10110, we can represent it as 116 bill, 08 bills, 14 bill, 12 bill, and 01 bills, a total of 22. The same logic applies when going from base 10 to base 2. You split up the number you want to convert into powers of 2 and set the corresponding bits to 1's, leaving the rest as zeros. One more example. Various rules that exist in decimal translate into binary, like when you multiply a number by 10, you just add a 0 to the end. Similarly, in binary, adding a 0 to the end multiplies the number by 2. Or how we can tell whether a number is odd or even by looking at the last digit. If the least significant bit is a 0, it's even, and if it's a 1, it's odd. Okay, so we know how base 10 and base 2 work, but there are infinitely many base systems, each having a different number of available digits. The other most commonly used base is base 16, called hexadecimal. Its 16 digits go from 0 to F, like this. Using the bill analogy, a number like 3B6 could be split into 6 1 bills, 11 16 bills, because B is the 11th digit, and 3 256 bills. 256 because that's 16 to the power of 2. Hexadecimal has 16 states and binary has 2 states, and since 16 is a power of 2, that means that every 4 binary bits can be easily converted into one hexadecimal digit. Just split the bits into blocks of 4 and turn each block into hex. As a result, hexadecimal is often used when presenting a lot of binary data. That way you don't have to be looking at a giant wall of 1's and 0's. You might have seen hexadecimal used to represent color, where 6 digits represent red, green, and blue components. As a fun fact, YouTube's video IDs are encoded in base 64. Base 64 means 64 different digits. Here they are. If you are in a browser, look at the URL. You can see the video ID after the V key. And that concludes the video.